Hey guys, today we're going to learn about something called the definite integral. Now, in our previous lesson, we learned about the indefinite integral, meaning that when you integrate a function that represents the antiderivative of the function, or f of x. Now, a definite integral looks a little bit different. You'll see it that you have your integration symbol, and then you're going to have here two numbers. These are called the limits of integration. And what that represents, so you can see a picture, is if you have your function f of x, so this curve right here, and you're given your limits of integration as a and b, or whatever numbers, then what this is going to represent is the area underneath the curve on that interval. So this would be x is equal to a, x is equal to b, and then we would calculate the area that is underneath that curve and bounded by the x-axis. So let's have a look at what that looks like and how we can go about to solving it. So here we have this f of x, and we're going to use the graph of f of x to evaluate for the integral from -2 to 8 of f of x. So notice that here, this f of x, this is my function here. So when you integrate it, I don't have an equation, so I can't apply what we did in our previous lesson. So we need to find the area. So the area again is that which is from the function to the x-axis. So here's my function starting at -2. And then up until here where 0 is, this is my x-axis, right? So my area is going to be this section here, right? Function and the x-axis, and then this section here. So these integrals that have these limits of integration, you're going to have an actual numeric answer, like you're going to get a number. So let's see how we get that. We all know geometric formulas for like triangles, squares, rectangles, trapezoids, circles. We need to know the formulas to finding the area of those particular shapes, because those are the shapes that we're going to see. So if you have area, like in this section right here that is below the x-axis, that area is going to be negative. Now this, as you can see, is a triangle. And the area of a triangle is 1/2 times the base, I'm going to call this the base, which is 2 units, times the height, which I'll call this the height, which is 2 units. Now above the x-axis, we have a trapezoid. Because that area is above, that means the area will be positive. And how you find the area of a trapezoid is 1/2 times the height of the trapezoid. So here is my height. So it's 1, 2, 3, 4 units, times base 1, so the length of your first base. I'll call this one here my base 1, which is 8 units, plus base 2, which is the one that's above, so which is 2 units. As a reminder for trapezoids, you're always going to have a pair of parallel sides. Those are your base 1 and base 2. Which one you call base 1 and base 2 does not matter, but these are my parallel sides. So those are my bases, and the height is perpendicular to those bases. So that's why I chose this line right here. So now that I've set up my area, I'm going to go ahead and figure out what this number is. We have here -1/2 times 2, which will cancel, and we're left with the 2, so -2, plus 1/2 times 4 is 2, times 8 plus 2, which is 10. And this gives me -2 plus 20, which is equal to 18. So this is the value of this particular integral. Now this coincides with something called the fundamental theorem of calculus, or you can call it the FTC. Now in order to apply this theorem, your function has to be continuous on the given interval and differentiable on that same interval. And what the fundamental theorem of calculus says is if you have the integral from a to b of f of x dx, so my definite integral, that's going to equal to capital F of b minus capital F of a, meaning the antiderivative of f of x. So there are two ways of calculating definite integrals, either one using geometry or two using the FTC. We're going to be doing both so you can see how they work together. So here we have our function, negative 2x plus 3, so this line here. And we're going to evaluate both ways using geometric formulas and using the FTC. So here we have the integral from negative 2 to 1 of my function. So here's my graph. So we're going from negative 2 to 1. By the way, our limits of integration, it's always the lower number on the bottom and the higher number on the top. So the area would be from here to here, again, bounded by that x-axis. And you can see that what we have here is a trapezoid. So let's find that area. The area of a trapezoid is 1/2 times the base, times the height. So here are my parallel bases. So this particular trapezoid is on its side. So my height will be the perpendicular side, which is this right here. So that's 1, 2, 3 units. Times base 1, I'll call this one base 1, which is 7 units, plus base 2, which is 1 unit. So this gives me 1/2 times 3 times 8. 3 times 8 is 24, and half of 24 is 12. Now we're going to calculate this same definite integral but using the FTC, and you're going to see how we get the same number. So when you have your limits of integration here, we're just going to set that aside for a second. We're going to integrate here this function. So we're going to apply that rule where you add 1 to the exponent and divide by the new exponent. So this will be negative 2x squared over 2 plus 3x plus c. Now, I'm doing it with the c for now so you can see what's going to happen. But whenever you're evaluating a definite integral, you do not need to use the plus c at the end, and you're going to see why. Now, in terms of notation, once I've integrated, you are going to show that you are applying the FTC by putting a bar, and then on that bar you're going to put your limits of integration, starting with negative 2 on the bottom and 1 on the top. So what this means is that we have already integrated, and now I'm going to evaluate this using these two numbers. So let me just rewrite this in a simplified manner. So this is negative x squared plus 3x plus c, and we're evaluating that from negative 2 to 1. So the FTC is f of b minus f of a. The top number is b, the bottom number is a. So what we're going to do is we're going to take our top number and we're going to plug it in for the x's. So it'll be negative 1 squared plus 3 times 1 plus c. Remember, c is some constant. I don't know what that is. It's not x. So that part is done. Minus now f of a. So now I need to plug in the negative 2. But we need to subtract everything that we get once we plug in the negative 2. So I'm going to have to remember to open a parentheses and then plug in the next number. So this would be negative 2 squared plus 3 times negative 2 plus c, close parentheses. Now let's evaluate this as much as possible. 1 squared is 1, and then we have the negative, so negative 1 plus 3 times 1, which is 3, plus c, minus negative 2 squared is 4, and the negative on the outside makes it minus 4, minus 6, plus c. Let's simplify one more time. Negative 1 plus 3 is 2 plus c, minus negative 4 minus 6 is negative 10 plus c. Now we're going to distribute the negative. And we get 2 plus c plus 10 minus c. See, look at my c's. They cancel out. That's why when we're doing definite integrals, we don't need to include the plus c when we integrate. And finally, 2 plus 10, we get 12. And you can see that it's the same value that we got over here using geometry. Let's look at a couple more examples, but we're still using the same exact function. So we don't need to reintegrate. We've already done this. We know that this integral is going to equal to negative x squared plus 3x. And that's for both of these because they're both the same. Now, here we're going to evaluate from 2 to 5. So here's the 2 and here's 5. So it's always, again, the function bounded, the area bounded by the function and your x-axis. So it's this section here, which again, we have another trapezoid that is on its side. So we're going to get that area. Now it's also below the x-axis, so keeping in mind that if it's below, the area will be negative. So that's 1/2 the height, which here are my parallel sides, so the height is perpendicular, which is this right here, which is 3, times base 1, I'll call this one base 1, which is 1, plus base 2, which is 7. Coincidentally, it's the same trapezoid that we did earlier. So this is going to equal to negative 1/2 times 3 times 8, which this is 24, and then divided by negative 2 would give me an area of negative 12. Now let's see if we get the same thing by using the FTC. So this is my integral, right, once I integrate it, and we're going to evaluate this from 2 to 5. So we're going to plug in the 5 first. So negative 5 squared plus 3 times 5 minus, now when I plug in the 2. So I'm going to open my parentheses and plug in the 2. So that's negative 2 squared plus 3 times 2. Negative 5 squared is negative 25 plus 3 times 5 is 15. Minus 2 squared is 4, and then the negative on the outside, so negative 4 plus 6. Negative 25 plus 15 is negative 10, minus negative 4 plus 6, which is 2. And negative 10 minus 2 is negative 12. So you see how we end up with the same answer. Now let's look at this last one here. Again, same function. We're evaluating from negative 1 to 4. So here's negative 1. This is my area that is above the x-axis. And then this is until 4, which is my area below the x-axis. Now you should notice here that these triangles are identical. We have here that the base is 1, 2, 3, and the height is, well, 1, 2.5. And then 1, 2, 3, 4, 5. And then here it's 2.5 and 1, 2, 3, 4, 5. I don't even need to calculate this area because this is going to be positive area. This one is negative area. So if I add this area and then subtract the exact same area, we're going to get that the answer is 0. So let's see if that's what we get by applying the FTC. So let's go ahead and we're going to evaluate this from negative 1 to 4. Plugging in the 4 first, we get negative 4 squared plus 3 times 4 minus, open my parentheses, plug in the negative 1, so negative 1 squared plus 3 times negative 1. 4 squared is 16, and then the negative, so negative 16 plus 12 minus negative 1 squared is 1, and then the negative on the outside makes it minus 1 minus 3. Negative 16 plus 12 is negative 4 minus negative 4. And a negative becomes positive, so this is negative 4 plus 4, which is equal to 0. And you see how it matches. So that's basically the FTC and using geometry to find that same exact integral. It just depends on what's given to you. If you're given the graph, you know to integrate, we're going to take the area. And if you're given the equation, you know that you're going to integrate and then apply the FTC. Now, just to wrap up what we looked at, the integral from a to b of f of x dx, that is the area of the region bounded by the function and the x-axis. If the area that you get is greater than 0, that means that the region that we're looking at is going to be larger above the x-axis than below, because if it's greater than 0, that means that the area is positive. So you're going to have the majority, if not all of your area above the x-axis. Versus if the area that you get is negative, that means that either your area is all below the x-axis or the majority of the area is below the x-axis. And finally, if the area is equal to 0, that means that the area above the x-axis and the area below the x-axis are the same and therefore would cancel each other out. So just to make sure that we understand that, let's say we are given this particular function, and you can see that I've already shaded in those particular areas. If I were to evaluate from negative 3 to 1, that is from here to here, you'll notice that the majority of the area is below the x-axis. That means that this integral, I'm not actually going to calculate, I'm just trying to figure out what sign it would be. That particular integral would be a negative answer. So it's a nice way of checking your work if you're given graphs. If you find that your area, you get a positive area, but yet the majority of your function is below the x-axis, then you know that something went wrong. Versus now, if we're looking from 0 to 4, that would be from here to here. You'll notice now that the majority of the area is above the x-axis. So I know that this particular integral is going to be a positive number, again, because that area is above. Now, let's just practice. Here we have a particular function, and we're going to be using our geometry to find the value of these definite integrals. So here we have the integral from negative 4 to 4 of f of x dx. And the function that we're given here, this is f of x. Again, I'm using geometry because I was given a graph. So I have no other choice. I have to take the area. Versus if I was given the equation, then I could apply the FTC. Or do both if you want to verify your answer. So let's see, from negative 4 to 4. When we're calculating the area, we have to keep track of our signs and our shapes. First, here we have from negative 4 to negative 2. This is a triangle. And just in case, I put all of our most useful geometric formulas that we would be using for this particular lesson. So let's start by calculating the area of this triangle here. So that triangle is going to be negative area, so it'll be 1/2 times the base, I'll call this my base, which is 2, times the height, which is 1. Then we have this semicircle. So the area of a circle is pi r squared, but because we only have half of a circle, I'm going to subtract, because the area is below, half the area of the circle, which is pi, and then the radius, which is from the center to the edge, which is 2 squared. Then the last bit of my area, you can see it's this triangle here, and that's above the x-axis. So I'm going to add that area, which is 1/2, the base, which is 2, and the height, which is also 2. Now we just simplify this and evaluate. This 1/2 and this 2 will cancel. So we have -1 minus 2 squared is 4 divided by 2 is 2 pi plus this 1/2 and this 2 will cancel, leaving me with 2. -1 plus 2 is 1 minus 2 pi. And you're not expected to actually put this in the calculator or anything, so this would be our answer. Now let's try this again, but now we're evaluating from 0 to 5. So I'm just going to erase this here just so that we can see our new area. From 0 to 5 is from here, this is 0, and then 5 over here. So we got to see what shapes we have. Here we have a quarter circle, then we have this triangle, and then we have a trapezoid. So let's go ahead and start working on adding up these areas. This quarter circle is below, so minus. Now because it's a quarter of a circle, I'm going to divide by 4, so -1/4 pi, and the radius is still 2 squared, plus the area of this triangle, which I already did the area of this triangle. That was this part right here, because it's 1/2 times 2 times 2, which is 2, plus the area of this trapezoid, which is 1/2. Now the height, which is 1. Again, because it's perpendicular to my bases. So these are always the bases of the trapezoid because they're parallel. And now base 1 plus base 2. Base 1 I'll say is 2 plus base 2, which is 1. So here what we have, 2 squared is 4, divided by 4 is 1, and it's negative, so -1 pi plus 2 plus, here we have 2 plus 1 is 3, times 1 is 3, times 1, 3 over 2. Now I do need to combine at least these two here. So I'm going to rewrite this 2 as -pi plus 4 over 2 plus 3 over 2, which gives me -pi plus 7 over 2. So that's how we find the definite integral using geometry. Now let's go and look at an example of when I would have to use solely the FTC. So here we're going to evaluate the integral from 1 to 4 of 2x plus 3 over x squared. And remember that we cannot, there's no quotient rule for integrals, so I need to rewrite this particular integral in polynomial form. This is the same thing as saying the integral from 1 to 4 of 2x over x squared plus 3 over x squared. So I split up my fraction since everything is being divided by x squared. And now I'm going to rewrite this with negative exponents if needed in order to integrate. So again, 1 to 4. 2x over x squared, I would subtract those exponents, so that is 2x to the -1 plus 3, and now I'm going to bring up the x, so x to the -2. Now let's go ahead and integrate this particular function. If I add 1 to this exponent, I get 0, but then I cannot divide by 0. So this is an example of ln. And this 2 is just going to tag along. So this is going to be 2 ln of x. And just in case if you need to see that, that is this, 2 over x. And I can move the 2 to the outside, which is 2 integral of 1 over x, which you should recognize that as the derivative of ln. So 2 ln x plus 3, I'm going to add 1 to my exponent here, which will be -1, divide by the new exponent. And because this is a definite integral, I don't need to put the plus c, and I'm going to evaluate this from 1 to 4. I'm going to rewrite this now to simplify and also write it with positive exponents so that I can actually get those numbers. So this is 2 ln x minus 3 over x, and I'm evaluating that from 1 to 4. So now we're going to apply the FTC. We're going to plug in the 4 first. So 2 ln 4 minus 3 over 4. Minus, now I'm going to plug in the 1, so I'm going to open my parentheses. 2 ln of 1 minus 3 over 1, which is 3. Here I can't really do anything with that yet, so I'm just going to leave that. Minus the ln of 1, that's 0. So 2 times 0 is going to be 0. So what we have is 2 ln of 4 minus 3 over 4 minus negative 3, which will then become 2 ln of 4 minus 3 over 4 plus 3. You're not expected to know what this is, so we can just leave that as 2 ln of 4. But I do want to combine this, so I'm going to rewrite this as 2 ln of 4 minus 3 over 4 plus, I want to put this over 4, so that'll be 12 over 4. And so my final answer would be 2 ln of 4 plus 9 over 4. So that's using the FTC. Let's try a couple more examples. Here I want to evaluate this integral from negative 1 to 2 of 2x minus x squared. So first we're going to integrate. 2x would be 2x squared over 2 minus x to the third over 3, and I'm going to evaluate that from negative 1 to 2. I'm just going to simplify this because these 2's here will cancel. So x squared minus x to the third over 3. And please do not forget the bar with your limits of integration, just so that it's easy to keep track of what you're doing. So you always plug in the top number first. So this would be 2 squared minus 2 to the third over 3. And now we subtract when I plug in the lower limit. So that's going to be negative 1 squared minus negative 1 to the third over 3. Let's evaluate. 2 squared is 4 minus 8 over 3 minus negative 1 squared is 1. Negative 1 to the third is still negative 1 because it's an odd exponent, but then we have that minus, so it becomes plus 1 over 3. Now before you start combining everything by getting common denominators and such, what I like to do as kind of like a little tip is that I simplify like each half of what I have. Like here I am not going to combine this quite yet because this is a whole number and this is a fraction. Here is a whole number and then a fraction. But I do notice that these two here have the same denominator. So I'm going to distribute this negative first, and you're going to see what's going to happen. Now what I can do is combine my whole numbers together. So 4 minus 1 is 3. And then I'll combine my fractions together that I don't need to find a common denominator for. So negative 8 over 3 minus 1 over 3 is negative 9 over 3. And this I can actually divide, so I don't even need to worry about that. This is going to be 3 minus 9 over 3, which is 3, and 3 minus 3 is 0. Let's try with this last one here. We're integrating from 0 to pi of 2x plus cosine x. So the integral of that, 2x, is x squared, as we did that here, plus sine x. And I'm going to evaluate that from 0 to pi. Plug in the pi first. We get pi squared plus sine of pi minus, now I plug in the 0. 0 squared plus sine of 0. Pi squared we're going to leave as pi squared. Plus sine of pi is 0. Minus 0 plus the sine of 0, which is 0. So what we end up with here is just pi squared. And that would be my answer. Now let's have a look at how we would apply the FTC using charts. So here we have a chart of values. We have several x's, and then we have the function values for f of x, f prime, and f double prime. So if we're going to use the FTC, keep in mind here that when we integrate f prime of x, this is going to equal to f of x. And because this is a definite integral, I don't need to put the plus c, but we are going to evaluate that from -3 to 1. So now we plug in the first value, so f of 1 minus f of -3. And here's where I look at my chart. F of 1 is -2. F of -3 is 4. And -2 minus 4 is -6. Now over here we have the integral from 1 to 5 of f double prime of x. When we integrate, this is 3, remember a coefficient just tags along, and the integral of f double prime is f prime. And we're evaluating that from 1 to 5. So we plug in b, so this is going to be 3 f prime of 5 minus 3 f prime of 1. We look at our chart for these values. F prime of 5 is 2, so 3 times 2 minus 3 times f prime of 1, which is 0. So here we get 6 minus 0, so 6. Now in these bottom two, our functions we have a little bit of a combo. So when we integrate this, go in order like we do with polynomials. Integrate the first plus integrate the second. So this is going to be f of x plus f prime of x. And we're going to evaluate that from -1 to 3. So first we're going to plug in the 3. So f of 3 plus f prime of 3 minus, now I'm going to plug in -1. And because this is not just a solo function, I'm going to make sure to open up a parentheses so I don't forget to distribute that negative. So now I plug in the -1. This is f of -1 plus f prime of -1. Now we're going to plug in these numbers from the chart. F of 3 is 1. F prime of 3 is 3, so plus 3 minus f of -1 is 0 plus f prime of -1 is 1. So we have here 1 plus 3, which is 4, minus 0 plus 1, which is 1, and 4 minus 1 is 3. For this last one, we have the integral from -3 to 3 of 1/2 f prime plus 2 f double prime. So when we write this out, remember again, these are coefficients. They're just going to tag along with our integral. So this is going to be 1/2. The integral of f prime is f of x plus 2. The integral of f double prime is f prime of x. And I'm going to evaluate that from -3 to 3. So now let's plug everything in. We're going to plug in the 3 first. So 1/2 f of 3 plus 2 f prime of 3 minus, open my parentheses, 1/2 f of -3 plus 2 f prime of -3. Now let's plug in the numbers from the chart. We have now 1/2 f of 3. F of 3 is 1 plus 2 f prime of 3, which is 3, minus 1/2 f of negative 3, which is 4, plus 2 f prime of negative 3, which is negative 2. 1/2 times 1 is 1/2, plus 6, minus half of 4 is 2, and 2 times negative 2 is negative 4. So we got 1/2 plus 6 minus 2 minus 4 is negative 2. So because it's minus negative 2 will be plus 2. So 1/2 plus 8, which now I want to combine this. So I'm going to put 8 over 2, which makes it 1/2 plus 16 over 2, which gives me my final answer of 17 over 2. Now let's look at some properties of integrals. If you have an integral that is from a to b of f of x plus or minus g of x, kind of like what we saw here in these last two, how you have one function plus another, then you can always separate the functions and integrate f of x and then add or subtract whatever the sign is, the integral of g of x. Here, notice that my limits of integration are reversed. Your lower limit should always be on the bottom, meaning the smaller number should always be on the bottom. So instead of from a to b, if it's read from b to a, then what you would do is switch those limits of integration back, but then that would mean that the answer to that integral would be the opposite sign, hence the negative. Now in this next one, if you have an integral from a to b of f of x, plus the integral of b to c of f of x, then that's going to equal to the integral of a to c, so the entire interval. So kind of think about it like this, right? If you have here is a, and here is b, and here is c. If you're getting your function, you're getting this area. So that's this first one. And then you're going to add this area to it. You see how they're connected? I can just combine these and create one integral from a to c rather than having the two separate. Now here, this is one that we've used before. If you are integrating from a to b of k f of x, where k is some coefficient, then if you kind of don't want to deal with that coefficient right away, you can always take it and move it to the outside of the integral, since it just tags along anyway. The only caveat here is that the k has to be multiplied to the entire function, not just to a piece of it. So like, for example, if we had 3x plus 1, I cannot move the 3 to the outside because that 3 is not multiplied to the 1 as well. Versus if I have the integral of 3x plus 1, then this 3 is being multiplied to everything, so we can move the 3 to the outside. And our last property of integrals is if you're integrating from a to a, meaning it's the same exact number, that answer will be 0 because there will be no area there because it's just one x value. Now these last two apply to symmetry. So if you have an even function, meaning that it is symmetric along the y-axis, much like here in this diagram, then that would mean that if you are integrating from negative a to a, provided that those numbers are the same, it's just one negative and one positive, then if you only know half, like from 0 to a or negative a to 0, then you can just get the area of one side and multiply it by 2 because the other side is going to be identical, which is what these two integrals here are saying. Now, if you have an odd function, meaning that it's symmetric along the origin, you can see here, and this is something that we saw earlier, you'll have area above the x-axis and area below the x-axis that will be identical. And if that's the case, if you're integrating from negative a to a, again, provided that these two numbers are the same, just opposite signs, then this integral would equal to 0 because this area would cancel out with this area here. Now let's have a look at how we would apply these properties. If the integral from 0 to 3 of f of x dx is equal to 6, and the integral from 3 to 7 of f of x dx is equal to negative 8, determine the value of each of the following definite integrals. So for this first one, we have the integral from 0 to 7 of f of x dx. You'll notice that what you have here, you have from 0 to 3, and then connecting 3 to 7. So this is going to equal to the integral of 0 to 3 of f of x dx plus the integral from 3 to 7 of f of x dx. These values are given to you here. From 0 to 3 is 6, plus 3 to 7 is negative 8, and 3 plus negative 8 is negative 2. Now over here we have two things going on. One, always look at your limits of integration and make sure that they are in the correct order. I notice that they are in the opposite order, so I'm going to switch them back. So I'm going to put the lower limit on the bottom and the upper limit on the top, but then that would mean that this would be negative. Additionally, I have a 3 here, a coefficient that is being multiplied to f of x. So I can take this 3 and move it to the outside. And then this would be written as negative 3, the integral of 3 to 7 of f of x dx. I have this. This is what was given here. So this is going to equal to negative 3 times the integral from 3 to 7 of f of x, which is negative 8. And negative 3 times negative 8 is 24. Now over here we have a bit of a combo. We have here this 2 minus 4 f of x, and we want to integrate from 0 to 7. Now these are two separate functions because this 2, we don't have anything here that includes a 2. So what I'm going to do is I'm going to separate this integral. So this is the integral from 0 to 7 of 2 dx minus, and this 4 I can move to the outside, the integral from 0 to 7 of f of x dx. Like that, it allows me to evaluate what this is, and then this I actually already found up here. So this is going to be, the integral of 2 is 2x, and I need to evaluate that from 0 to 7. Minus 4, and the integral from 0 to 7 of f of x, like I said, we got here, is negative 2. Now I'm going to plug in the 7. 2 times 7 is 14, minus 2 times 0, which is 0, minus 4 times negative 2, which is plus 8. And 14 plus 8 is 22. For this last one, the integral from negative 3 to 3 of f of x dx, if f of x is an even function. If it is an even function, again, that's that it is symmetric along the y-axis. So pretending that this is my f of x, this is the negative 3, this is 3. Both of these areas would be identical. So I don't need to find the entire thing, I only need half of it. And you'll notice that here we have from 0 to 3, which is this half here. So this is going to be 2, because again, the other side is identical, the integral of 0 to 3 of f of x dx. So we got 2, and that integral is 6. So 2 times 6 gives me 12. Now let's have a look at how we apply these properties using graphs. For this first one, what we have here is from 0 to 3. So we are going from here to here. So you are going to separate this using whatever shapes you see. So I notice I have a quarter circle up here, and then I have a trapezoid down here. You can also do this quarter circle, you can do this rectangle, and then the triangle. It's completely up to you. But I'm going to stick with my trapezoid, just so that it's one less formula for me to use. So the quarter circle is going to be 1/4 pi, and then the radius, which is 2, so 2 squared, plus, now for my trapezoid, that's 1/2 times the height of my trapezoid, which is 1, times base 1, which is 2, plus base 2, which is 3. So what we have here, 2 squared is 4, divided by 4 is 1, times pi is pi, plus 1/2 times 1 is 1/2, times 2 plus 3, which is 5. So this gives me a final answer of pi plus 5/2. Now having a look here from 0 to 4. So now we're extending. We're still starting at 0, but we're going all the way to 4. And what you should notice is that you have these two areas here, these two triangles, are identical. And one is above the x-axis while the other is below. So these two are going to cancel out. So in order to find the area of from 0 to 4, I really only need this quarter circle, which I found earlier, and this rectangle. So for the quarter circle, this is what we did. We had the 1/4 pi 2 squared, which equaled to pi, plus the area of this rectangle, which is 2 times 1, base times height. So this is equal to pi plus 2. Now for this last one, we have the integral from -3 to 3 of f of x dx. Now notice that if I erase this a second, if we're going from -3 to 3, first of all, you should notice that this is an even function because it is symmetric along the y-axis. This side is the same as this side. So I don't really need to find the area of everything once again. Instead, this is going to be double of the area from 0 to 3. And I'm using 0 to 3 because I did that one earlier. So this is going to be 2, and then this integral that we got, which is pi plus 5/2. And distribute the 2, we get 2 pi plus 5. Now, for the last topic we're going to look at with our definite integrals is how to find a function value from a definite integral. So here we are given the graph of lowercase f of x. And we're told if capital F of -3 is equal to 5, what is the value of capital F of 4, where capital F of x is the antiderivative of f of x. So here's the thing with these questions. We are looking for particular function values of our function, the antiderivative. But what we're given is the graph of the derivative. So what that means is that we're going to have to integrate in one way or another. To figure out how to set this up, I know at least that it is an integral. And we're going to integrate f of x dx. But that's not enough. We need our limits of integration. How you can determine what those limits of integration are is if we are looking for f of 4, 4 must be included. But we are also given f of -3. These x's are my limits of integration, and always put them in order. This is my lower number, so I'm going to put -3 on the bottom and then 4 on the top. And this is going to equal to capital F of x evaluated from -3 to 4. And the reason why we do this is because if I use my geometry to get this integral, like we've been doing, that's going to equal to capital F of 4 minus capital F of -3 by applying the FTC. So essentially, we are combining here our methods of integrating using geometry and the FTC at the same time. So this part here, we're going to use the graph and we're going to get a number. And then here we have f of -3 that we can replace. place, and that would allow me to solve for capital F of 4. So let's start off with this side. Let's look at our shapes. We are starting from -3 until 4. And so here on this side, what I have is a trapezoid. Then here, this is the tricky part. I have this quarter circle, but the area is always from the function to the x-axis. So it is this part here. We'll get to how to solve that area in a minute. But over here, I have this triangle and this triangle, which are identical. So these two triangles I don't need because they're going to cancel each other out. So these two I can just ignore. Now let's look at how to set this up. The trapezoid we know. It's 1/2 times the height, which is 3, times base 1, which is 3, plus base 2, which is 1. Now over here, in order to get this area, let me draw it over here so you could see. What we're going to do is we're going to get the area of the rectangle. And then what we're going to do is we're going to subtract the area of the semicircle. And see, when I subtract it, what's left is the pink here, which is what I'm looking for down here. So I'm going to add the rectangle, which is 2 times 1. And I'm going to subtract the semicircle, which is 1/2 pi, the radius, which is 1 squared. And that's going to equal to capital F of 4 minus f of -3, which is 5. Now let's start working this out. 1/2 times 3 times 4 plus 2 minus 1 squared is 1, so this is going to be minus pi over 2. And that equals to f of 4 minus 5. 3 times 4 is 12, divided by 2 is 6, and so 6 plus 2 is 8. So to solve for f of 4, all I have to do now is add the 5 over to the other side. So f of 4 is going to equal to 13 minus pi over 2. Let's try that one more time. If f of 9 is equal to -2, what is the value of f of -4, where f of x is the antiderivative of f prime? So here is my f prime. So what I want to do is I'm going to set up my integral. Since I'm given f prime, inside is going to be f prime because I'm solving for f of x. Then my limits of integration, that's going to be the x values that are given here. Always writing them in order, so the -4 goes in the bottom, and then 9. And this is going to equal to f of x evaluated for -4 to 9. So let's have a look at what we have here, what kinds of shapes. We're starting here, and we're going up to there. Now we have this triangle here, and then here we do have one giant triangle. So it's up to you how you want to approach this. You can do this negative area, but then this part here would cancel out with that area. So we can basically ignore this section. Then here I have a trapezoid, and then a triangle, and then this semicircle. So for the trapezoid, that's 1/2 the height, which is 1, times base 1, which is 2, plus base 2, which is 3. Trapezoid done. plus triangle, 1/2, base 1, which is 2, well, base, and then the height, which is 3, plus semicircle, 1/2, pi. This is the center of the circle, so the radius is 3 squared. And that's going to equal to f of 9 minus f of negative 4. Let's start working this out here. 1/2 times 1 is 1/2, times 5 is 5/2. Plus, here the 1/2 and the 2 will cancel. So 3 plus 1/2 pi times 3 squared. 3 squared is 9, so this is going to be 9 pi over 2. And that's going to equal to f of 9, which is the value that's given, so negative 2, minus f of negative 4, which is what I'm trying to solve for. Now, we can combine these two. So we can say that this is 5/2 plus 6/2 plus 9 pi over 2 is equal to negative 2 minus f of negative 4. I'm going to continue over here. 5/2 plus 6/2 is 11/2 plus 9 pi over 2 is going to equal to negative 2 minus f of negative 4. We're going to add the 2 to both sides. When I add 2, I want to combine it with this 11/2. So I'm going to make this 11/2 plus the 2, which is 4/2. Plus 9 pi over 2, and that's going to equal to negative f of negative 4. 11/2 plus 4/2 is 15/2. And our final step to solve for f of negative 4 is we're going to divide by negative 1 or multiply by negative 1, however you want to do it. So f of negative 4, and that's just going to switch on my signs, is going to be negative 15/2 minus 9 pi over 2. And that is your definite integrals and the fundamental theorem of calculus, or the FTC.